right? So before we get started, how many have a chance to attend any seminar during your undergraduate or have been during your undergraduate? Like, have you ever attend like seminar from your department? Maybe from other departments?
Yeah, I had like a climate change one.
And what do you think is the purpose of the seminar?
That's fun.
So do you know that the computer science department or the electrical engineering and computer science department in general, we have a seminar this semester? You're aware that we have that going on this semester? No? So how many receive my email, my spamming email every month about the seminar? Done? Okay. Well, how do you know if we have seminar within our department? Well, you go to Google, right? You type in CUA PECS seminar. And the first thing you see would be this link. Okay. And you can see that there are several events that happened in the past, and then some going to happen in the future, which is tomorrow. Right? And what is the purpose of this seminar? It's basically give you an opportunity to listen to the cutting edge research. So what you read from your textbooks probably has been done a couple of years ago, or perhaps 10 years ago, right? So now these researchers, or they are either faculty or scientists from other university or other institution, they're actively performing research. And it has not been captured in textbooks. So one of the objectives of seminar is basically allow you to understand what is the latest technology. What can you do to make it better? Okay. So now tomorrow we will have seminar. And if you are interested in how you can safeguard your privacy, for example, how many have using Instagram? How many using Facebook? How many using Twitter?
That's online.
So just exactly. So then what kind of social media do you use beyond those three?
Texting.
Texting. Okay. So that's good.
Snapchat.
So then do you ever concern about your text that leaking out to other media? Like for example, let's say you're using texting group chat. You ever concerned that someone could snooping or trying to read your text?
Like outside of the group chat?
Yes.
Not really. It's like someone else.
Do you think that it's pretty secure?
What do you mean? Like someone accepting a text or like someone taking a phone and
Or not really like someone staring your phone and looking at your text, but like while you are conversing with your friends, you're confident that nobody will see the content.
oh, I got nothing to hide, so if someone did see it.
Well, I think we're not getting to the point where like hiding stuff or not. It's just that you care about your privacy. And if that's the case, how do you protect your privacy? Okay. So basically, she's an expert in coming up with strategy to protecting privacy in the modern society. So that is basically just a 5-minute pitch for the talk tomorrow. Okay, but my ultimate goal again is in addition to doing research paper, now I want to show you that if you want to learn about the cutting edge research, you should consider going to either the CS seminar, school engineering seminar, or the department seminar. So it's going to broaden your knowledge. Okay, and the knowledge is limit or not? It's unlimited, right? It's always expanding. Okay. And if you, let's say you're going to go and do graduate school elsewhere, the format will be the same. Okay, you should go to the department website, and they always have seminar talk going on. Okay. All right, that being said, let's get back to this topic. Okay, data computing. So today we're going to talk about properties of context-free languages. Okay, so how many have read chapter 8? All right, it's fine, just making sure. If you are not, what would be your guess, what topic that we're going to talk here? Given that we did something similar to the regular languages.
So, like families, context-free.
Very good. What else? Pumping lemma. For what?
So the languages aren't context-free.
So far we said, oh, we could create MPDA, DPDA, context-free grammars, right? For a family of context-free languages. We haven't touched to a point where we're saying that, is it true that all the context-free languages that we can guarantee to generate either the PDA machine, or we could generate the context-free grammar for those languages? And how can we recognize a set of languages that are not context-free? So what does it mean if it's not context-free? Does it mean that it's regular language? No. Okay, and if not the case, then what can we describe those set of languages? Okay, so now the objective of, again, this chapter is going to explore, again, we're going to apply the pumping lemma to show that some set of context-free languages are not context-free. Okay, and then we're going to explore the closure properties, in a sense that suppose that you're going to do set operation for a set of context-free languages. Do you guarantee to get the context-free languages at the end, or do you get something else? Right? What if you do the union between two context-free languages? What if you do concatenation between two context-free languages? What if you do complement? What if you do intersection? Okay. So now think, do you think that we can get the same context-free languages if we do the intersection between two context-free? How many think that yes, we can?
I'll say yes.
So, okay.
Yes.
He's brave enough to say yes, he's brave enough to say no. Who thinks that if you take, let's say, L1 is context-free and L2 is context-free, and you take the intersection between the two, you always guarantee that the result of that operation will give you another context-free.
Wait, so it is an intersection and it's context-free?
No, it's a good question.
Well, when you have two context-free languages and you do the intersection, do you expect to get context-free languages at the language at the end, or you not gonna guarantee to get that context-free? So you stand by your.
I don't think that it would necessarily be context-free.
But again, from regular languages, we wasn't going to show that, right? From regular languages, we wasn't going to show that if you do the intersection Then you get regular languages at the end. So what insight do you get that say, huh, it's not possible for the context tree? Is that a hint? How do you know?
I said yes.
So you say yes because based on his heuristic search, right? I know that regular languages, if you bring them together, you're going to get regular language. The other two are saying that, oh, it may not be the case. I want to know your insight. How can you recognize that they are not? For those online.
I think I agree with Zach in saying that it should be, because I mean, I get that regular languages and context free aren't the same thing, but I think the rule might still apply.
So now we have 50-50. Again, I think it's at this point we just like suppose that you haven't heard of, I mean, have not finished reading the chapter 8. I just want to ask your thoughts.
You said the intersection between two context free languages.
Mm-hmm. So let's say you have L1 and L2. And they are context-free language. So L1 intersection with L2. Do you get context-free language or you are not? No cheating. Don't look at the chapter 8 yet. Just based on what we learned so far.
Mechanics like German, 1, 3, or 8.
Now you're saying, oh, don't look at theorem 8.3. So you read the book. That doesn't count.
Well, so if L1 and L2 distinct, right? So their intersection is 0. But like if the intersection of L1 and L2 is empty set, is the empty set context free?
Usually, an empty set belongs to the class of context free.
I don't think so. So I'm going to provide my answer to no. In that case.
Why not?
Oh, because empty set is regular language.
Exactly. And regular is a subset of context free.
Yeah.
So it's context free.
Oh, no, it is not good.
All right.
Wait, so the answer is yes.
I don't know. Let's find out. Let's find out.
Still 8.3.
Well, you just say that theorem 8.3, right? So let's find out. Okay.
I'm confused with the question.
Well, the question is, let's say you have two context-free languages, and you do the set operation, in this case, intersection. Is it always the guarantee that you're going to get a context-free at the end? Okay, so he still stand by his. But again, if L1 and L2 are regular languages, and you do the intersection, do you get a regular language at the end?
Yes.
Yes? Okay, how do you know?
But use the theorem.
Or either using theorem or how exactly you're going to do it, go about to solve it. Okay, now the same logic applies to context free. Place.
I was gonna say, like, you self-apply, you making a finite automaton that would accept the regular language.
Very good, right? He said, don't challenge me. I know how to construct finite automaton. Which is, he's correct. What about this guy? Context-free languages.
If you can construct it in PDA, that's a good news.
Very good. So now if he could construct an NPDA for this,
Oh, you can.
can you?
Yes.
Okay, so he's saying he can. Any other?
Yeah, because you just put them right next to each other, right? So like you have the MPDA for L1, and it goes through, and then the final state of L1 to like the initial state of L2 goes through that way.
Okay.
Right?
So we're going to talk about all these things, like we're going to talk about the complementation and whatnot. But then let's go back and do this quick review here, right? So basically what I'm trying to get at is the following. So let's say I have L1. Is it regular language or is it context-free language?
L1 is regular.
So Zach says regular.
It's regular and context free.
It's regular and context-free. Okay. So again, regular is much stronger observation than the context-free, right? Because the notion that if it's regular, meaning that you can construct a machine for it. For the context-free, you need to do extra step, right? But again, we know that regular language is a subset of context-free. But it's also correct that it's also context-free. Okay, so now for case L2, is it regular or context-free?
Context-free.
How do you know?
Because like if you make a push down a common stuff for that language.
Can you?
Yes.
Very good. Confident. That's what I want from you out of this class. Okay. What else can you show that this is not regular language? Pumping lemma. Okay. Any question up to L2? Okay, what about L3? Is it regular or context free?
It's context-free. It's I'm pretty sure it's neither.
Well, I mean, couldn't you have the stack symbol count the number of?
Well, like, I'm not really sure how exactly.
Yeah.
Yeah, how exactly it could because like you know.
Well, no. So you count the number of A's. Oh no, never mind.
Okay.
Yeah, I can't think of any.
See a lot of discussion in class. What about online class? Are you with us?
Yes.
Yes.
Yeah. You think that L3 is a regular language or is it context-free language?
I think it's a context-free language.
So what is the indication that you think that it's context-free?
I mean, we can prove to see if it's a regular language or not using either the pumping lemma or the pigeonhole one. So I guess we can check using that way.
Let's say if you're using pumping lemma, what is the objective that we're going to get out of that?
You can prove it's not regular.
Exactly. So right. So earlier we showed that using pumping lemma to show that it is not regular. Basically, it's allowed to eliminate that it's not regular. But it doesn't show us that it's going to be context free, right? So what is the indication that when we say that L3 is context free, what is the indication? Sure, that's true. That's not regular. That's an inherent properties for the fact that it's not regular language.
If it's context-free, we can create a derivation for it.
So how can we create derivation for this one? Anyone else? It's okay to be wrong, but you're gonna learn.
Can we just do what we did in like previously in L1 and L2? So then we say like S points to A, S, B, S, C, and then lambda as a new role.
That would work. You have,
So, go ahead, Zach.
if you have A, S, B, S, C, then second S, you plug in, you get an A, and then A would be equal to B. You have then all the A's and those, and all the B's and all the C's.
Exactly. Okay. So it's not derivation. He's saying that it's the indication for a language to be a context free is that he can create a context free grammar. And from the grammar, then we can derive a particular string to check whether it belongs to that language or not. Okay. What else can we conclude if it's context free language? Exactly. Can you show me how you construct the push down automaton?
A couple hours.
How you know you did a couple hours? I give you a week.
Can't do it. And do it, let it keep it.
Okay. So it's neither regular language or context free. Okay. So now let's revisit the pumping lemma. Now we're going to use the pumping lemma for showing if a language is not context free. Okay. So now there's 8.1 saying that suppose L is an infinite context free language. Then there exists some integer m such that any string W in the language L with the length of the string W's have to be greater or equal to the positive integer m. Then we can decompose or break it down into substring such that W is the string that we are interested in. Can be break into U, V, X, Y, Z. Okay. So at this point, how does it differ from the earlier pumping lemma for non-regular language? Now you have UV. Okay, that's the only difference. So now if we could do this, then we can further put an additional constraint that the length of Vxy have to be less than or equal to m. Okay. So from earlier pumping lemma, how does this differ from the earlier pumping lemma?
It was just xy.
Xy, right? And the length of Vy is greater or equal to 1, or it's not 0. Okay? So now, when it satisfies these three conditions, then we can apply the pumping lemma, right? We can represent that string in W such that U V to the I, X, Y to the I, Z. And this also have to be in the language L for all I. Okay. Well, what is the objective of the pumping lemma here?
Determine if the language is not context.
Exactly. Okay. So you need to show that if a language is not regular, you're using this.
No.
No.
Use another one.
Exactly. Why you need this bigger machine to show that the language is not regular? Just using a simpler one. Okay. But if you want to show that a language is not context free, then using this one. Okay. And again, the idea here is we're going to show by contradiction. Okay. Again, this slide basically is a recap of the previous slide. just show just a point here that we're going to use the contradiction to show that it's impossible to achieve these three conditions. Okay. And if you recall from a parsing tree, right? What does it mean if we have a parsing tree? What is the purpose of the parsing tree? Okay, instead of derive or using the instantaneous description, we just construct a parsing tree for to visualize the derivation. Okay, so what we're trying to show here is that you can using the parsing tree to illustrate, to understand the, in essence, the operation of the pumping lemma here. Okay, how? Well, you can see that if you remember the U, V, X, Y, and Z, right? So basically you have two substreams. That's allow us to derive the two leftmost and outmost substring, U and Z, right? And then you further can go down and derive another two substring T3 and T4. This allows us to derive substring V and Y. Okay? And then T5 is a substring that's allowed to derive X. Okay? So how do you know that this string would be in the language? We know that W is in the language, right? So now this string U, V, X, Y, Z will also be in the language, right? Now let's look at this example again. Okay, so now we're going to using this example to show that this is not context-free. Okay. So if you recall from earlier example of the pumping lemma for regular, non-regular languages, right? What is, in essence, what is the trick that we can show that if this is not context-free?
You have to pick the right string.
Exactly, you have to pick the right string. Okay. So now what is the first thing we do here? Using the same logic that we learned from the non-regular language?
Assume that L is context-free.
Exactly. Okay. Assume that L is infinite context-free. Okay, then what?
Let M be the pumping length, by the pumping lemma.
Okay. So now, if it's infinite context-free, I can pick a positive integer m. I can pick a positive integer p. I can pick a positive integer k. Doesn't matter. Here it's just using m for consistency with the textbook. Okay. So then what? So if I can, if I pick m to be a pumping length, given by the pumping length, what can I do next?
Well, next we should choose what string W is going to be.
Okay, so what W should we get?
W is equal to A to the M, B to the M.
Okay, well, you pick that one.
Well, because we're using M as the pumping length.
Okay, now A to the M, B to the M, C to the M. Any questions up to this point? Pretty clear, right? So then if we check the pumping lemma, 8.1, what can we do next?
I'll show that that's impossible.
Oh, not yet, not
You
yet.
have to decide what U, V, X, Y, and Z are.
But before that, is this in the language?
W is a set of L.
Oh, yeah. Yes,
It
yes.
has to be value of W is greater than or equal to M.
So first, let's make sure that this is indeed in L, right? What if someone say they pick A to the M, B to the M, and C, where M equal 1? Is this in L?
Yes.
Okay. So you can pick this one, or you can pick that one. Which one?
Unless there wasn't there, CDM was just.
Well, the thing is, we have to pick W strategically so that we can apply the topping lemma. If we pick this one, hopefully we're going to get to the contradiction. Okay? If we pick this one, it probably not going to allow us to get to the contradiction. But what my point here is that if I pick W is this guy, W2 is that guy, and W1 or W is this guy, can you see that they're both in the language L? Is this belong to, is it in L?
Not for all values in F, but if N equals 1, it is.
I'm just saying N equal 1.
Oh, yeah, it is. It is.
Okay. Question. All right, so now let's pick that line. And we know that is in L. Okay. So now what is the next thing that we should check beyond that this is in L?
The absolute value of M is equal to or 3M is greater than or equal to M.
The absolute is the length of W. Okay? Have to be what?
M plus M plus M.
Okay? That would be M plus M plus M. Right? And this would be 3M. Is it greater or equal to M? It's obviously greater, right? So this also is a very good pick. Excellent. So far so good. Okay. Now what?
W is equal to U, V, X, Y, Z.
Okay. Now you're trying to show that it is possible. Now we're trying to show it by contradiction. Okay? Now,
For I degree, so U, V, I, U, V, I, X, Y, I, Z.
okay? Then what?
Length of V, Y is greater than 0.
Okay? Then what?
The V, X, Y is less than or equal to M.
Okay? So all these three is pointing back to this guy, W. How do we decide to break down this string to come up the substring U, V, X, Y, Z? So
I think so. I think U equals A minus A to the n minus 1.
n minus 1.
E is equal to A. X is equal to lambda. Y is equal to B to the n minus 1. And then Z is equal to B to n.
Can I do this? Is it the appropriate split? Do you have contradiction? Do you agree with this split?
Well, so in this case, I think m has to be greater than 1. Oh, which is fine.
Well, let's stick with this guy, right? Okay, let's stick with this guy. Okay, now does it meet this condition? By greater than 0. What is b? B is a y b to my minus n. Yes, it's greater than 0. Okay, what about this guy? bxy. B is a, x is lambda, y is b to the n minus 1. Is it less than or equal to n? It is, right? So we got, so now this split is meeting all three things. Okay? So now, what is the last thing that we need to check? The pumping. Right? Now we need to pump with different I. Okay? How do we do that? So let's pick I equal to. Okay, now what do I get? U would be A n minus 1. Okay, B would be A. Right? X would be lambda. Y would be B minus 1, B minus 1. All right? And the rest would be, I'm going to erase this guy. Would be B C to the M. Right? So how can we simplify this guy? A to the M plus 1.
To m minus 2.
So M.
So what is your 2 minus 1 there? Because we still have the yeah, it will be 2 minus
Oh, you wait.
Minus 1.
the c to the n.
Yeah. Is this in L?
No.
No. Then what can we say?
That it is not.
This is not context free. Okay? Any questions? This again very similar to the pumping lemma for regular, non-regular languages. Here we should need to break it even a little bit further in terms of U and V. Okay? This is the only split that we need to do. What if you split it that way? Again, here it's showing you that there's multiple ways And we can split the W into U, V, X, Y, Z. Here's one way, there's another way. Okay? But then how do we know that we split them correctly? We split them correctly when we check back with these three conditions. All right? And they should meet these three conditions. But then when the moment we apply the pumping the I, right, and then we can show that there's a contradiction. Okay. Question?
So we're allowed to split like a letter in half technically, because we said like in the example it's saying a to the m over 2. So it's like we're splitting the a into multiple parts.
So the question is can we allow to split a to the m over 2?
Yes, because like in the set thing will be AM over 2, times AM over 2, which when added together would be A to the 2 over 2, which is just due to H to the M.
Right. Okay. Any other questions? Okay, so now it's very similar to the earlier pumping lemma. So here we also have another pumping lemma for the context free. So before that, let's say I have this example here. Can you show how we can, using the pumping lemma for the context free language, to show that this language L is not context free? Okay. So right now is 11:53. So I'll give you 2 minutes. rain is coming.
Yeah, no, it's supposed to get cold tonight. I looked at the weather.
Really? All right, so now who has already figured it out?
Those steps is female is contact grid.
Very good.
Then and is
Awesome.
and then so I said W was equal to A to the M, E to the M, W, A to the M, and
Why you pick this one?
Because it's similar to the last one. It's isolated, side isolated like and right, and then you come back and you get like
Okay. Did anyone come up with different split? I mean different string with different W? No? So you share the same, basically you will go to it.
nice.
That is mine.
Well, yeah.
Okay. Anyone else from the online class that if you come up with a different W?
I used the same one as Zach did.
So what W you think that, or what W did you pick? Besides this one. Cannot be the case. It's phenomenon. And everybody picking the same string. How is that possible? It's amazing. This is the only string that you guys came up with?
It's the microchip that they planted the broadcast out.
All right, I give you that. Okay, now, so then you can pick up with this guy. W with that guy. And you convince that that is belongs to, that is a member of L.
I hope so.
The hope is not good enough. You should convince that this is in L.
Yes.
Yes! We're not playing uncertainty here. We have to make sure that we get it right. Okay, it's indeed now. Okay, now what?
And so magnitude of the length of W greater than
Okay.
and then we have to now the next step U V X Y Z.
Very good. Now what is U going to be?
I see U
Use lambda. Anyone else? Okay, so that's good. So now you all pick the same W. Perhaps you probably split them differently. Okay, so if that pick U is equal lambda, what U do you pick?
I said that U equals A to the M over 2.
A to the M?
Yeah, over 2.
Over 2. Okay, now Zach, what is your
X is lambda.
X is lambda? What is X you're going to pick?
My X was. Wait, do we skip V or is it?
V, let's do V first. So lambda would be next. All right, UV.
My U is A to the M over 2.
V would be A to the M over 2. And what is your V?
Mine is A to the M over 2.
Yep.
My x is b to the m over 2.
Okay. What about y?
I think y was a to the
What about you, David?
Mine was also b to the m over 2.
my c was just b to the f, b to the f, b to the f.
And then my z was a to the m, b to the m.
Right. So now, being getting to normal, people split differently. Okay. Which one should we pick moving forward? Zach? Okay. What about, what are you pointing to him? Do you agree?
Yeah.
Okay. But before we pick, which one should we go forward? Do they all meet the condition that the length of what?
Pxy less than f. David, I think
Bxy
should be less than or equal to
less than or equal to
m.
m. Okay. So Zach saying that if we split the way that David split would not meet this condition. Someone else, besides David and Zach, convinced me that that is the case. So that I'm confidently going to put this on the final exam.
Like this exact problem?
Something similar. Please. Using this constraint, determine whether this, the way that we split this case number 1, this case number 2. Which one would meet this condition? Or they both meet this condition?
For sure, only one would.
How do we show this? How do we show this?
By adding to the list.
Exactly, just adding them together. Okay, so U will be lambda. Let's first test for case number 1. Okay, U will be lambda. X would be lambda. And Y would be.
Oh, is it uxy or dxy?
Which one are we testing? UXY or DXY?
I don't know. I thought we said v back like by
V? Okay, let's start V. VXY.
Is it v?
Yeah, it is.
Okay.
Okay, if it's V, then V would be A m over 2, X is lambda, and Y A m over 2, which is m, right? Less than, exactly equal m. So check. What about this guy? Okay, V would be A m over 2, X would be B m over 2, and Y would be B m over 2. All right, so now what is the length of this guy?
M plus M over 2.
M plus M over 2. Okay, comparing with M, what is the equality sign should we use? Greater.
And,
Aha. So now you can convince that if we split using case number 2, you'll not be able to satisfy this condition. All right? So now we're going to go with 1. Okay? Question. Okay? Now what?
Now I equals 2.
So we know that I equal 1 would be exactly this string.
Yep.
Okay, now let's do I equal 10.
Okay, I equals 10.
I equal 10. Do we use I equal 10?
Yes.
All right, let's do that. Okay, now what?
So U is still going to be
Lambda.
D is going to be 5M. X is still going to be lambda. Y will also be 8 and 5M.
Y would be this guy.
And then Z is going to be B to the N, A to the N, B to the N.
Question.
And that is not in the language because the language WW says first half of the string has to be the same as the second half of the string. First half of the string is A to the 10 N, B to the N. The second half of the string is A to the N, B to the N.
Exactly. This obviously is not allow us to get this equal the amount of string for the first half and the second half. Question? If we split in different way, is there more than one way we can take up? The answer is yes. Okay. So I can split it this way. U will be a m over 2. U will be m over 2 minus 1. Actually, we get AB. Where G equal m over 2. Y is m over 2 minus 1 is the half of the string. X1 out. Okay? Because U will be B.
Does that satisfy the condition?
Which condition?
The length of dxy has to be less than 10.
Let's check. Maybe I'm wrong. And B would be
M over 2 minus 1.
2 minus 1. X would be
So it's
A
M over 2 plus 1.
over 2. What is this? Is M over 2 plus 1, right? And
Y would be M over 2 minus 1 again.
M over 2 minus 1. Okay. Now, this guy, M over 2, cancel out. This is M over 2 plus M over 2. M, I have extra M over 2. That's wrong. Aha, I'm wrong.
That's like extra credit.
So I guess this won't come from.
It is read on a final.
But Professor, if you do it wrong, then like,
Well, the whole solution would give you the proof that it's wrong or it's wrong or it's right. Okay. So for those reading my slide earlier in this class, I can say that you cannot point out if you're not following it, you'll not be able to see it is wrong or right or wrong. Only Zach can figure it out. Okay. Question. Now you know what is the correct answer for that one by paying attention to this one. All right. Very good. All right. So now we also have the puffing lemma for linear languages. Okay. So again, the idea is the same. Let L be a linear language. Then there gives some positive integer M. Again, we're going to follow through that example. And we're using this to show that the infinite linear language is not context free. Okay. So now we know how to recognize context free languages. How can we show that a language is not context free? Okay. Now let's look at some of the properties when we do the set operation. So theorem 8.3 saying that the family of context-free languages is closed under the union operation, concatenation operation, and stock closure.
Yeah, that's right.
How do we prove this? How do we prove that these features are correct? What trick we use? What method we use?
For union, we can use push down automata, right? Because from the starting state, we can have two lambda transitions.
So Nick proposed to using push down automata. Do we want to use Nick approach or using different approach? Grammar. Using grammar. Easier. I know. Come down. Using grammar. Okay, push down automata is fine. Because that is one of the two techniques that we learned about how the context-free languages. But using grammar to show that these two are the case. Okay, using simpler method because you don't have a lot of time. Okay, now to show that they are closed under the union, what we do is we are assuming that they generate the two different grammar, G1 and G2. Okay, and we further assume that V1 and V2 are disjoint. What does it mean?
It means that they don't share any languages in common. Like the intersection between the two of them would result in an empty set.
Would be an empty set. When you look at the variable set, you should get an empty set. So now create a new variable S3. What is S3? The starting symbol for grammar 3. Okay. Now we can show a new grammar G3, which satisfies the previous 2 points. Okay. Now the B3 set would have what? What does it mean? The union. Collect them all. Collect all the variables from V1, V2, and adding the start symbol for the grammar 3. Then create T3. What does it mean again? Okay, so I'm going to add the terminal symbols from grammar 1 and grammar 2. Put them into grammar 3. Okay? What do you think of the production will look like?
It's a union of P1 and P2 with an additional production. Two additional productions that S3 goes to S1 and S3 goes to S2.
Okay, very good. Okay, so we're going to basically collect all the production from P1 and P2, put them to P3. Then add one more addition, production from S3, addition to S1, or addition to S2. Okay. So now, clearly, G3 is the context-free language. And clearly, the union of L1 and L2, when you take the union between the two, then you should get a context-free. Extremely strong proof here, right? How about concatenation? Or the same concept, right? Assume that L1 and L2s are generated by G1 and G2, and B1 and B2 are disjoint. Okay, create a variable S3, S4 here, create a new grammar, which is not in the union between the B1 and B2. Okay, now construct a new grammar G4. Okay, so what is the property of G4? Very similar to the previous case. The terminal set also very similar to the previous case. The production also very similar to the previous case. Okay, so what do you think the last rule that we need to add to P4? If you want to achieve L1 concatenate L2.
Well, so you need to have the S4 goes to S1. And then you need whatever the after each book, you need something that goes from the final state of P1 to S2.
Okay. This is what we need.
Oh, for that, yeah.
So from this problem, I can make one question in the final exam. And I let you guess what can I change from here that can be a question. Okay. So clearly G4 is context free. Okay. What about star closure? Do we need two languages to show this star closure? No, right? Suppose let's say assume L1 is context free, we can derive G1 grammar. They're going to create a new starting variable S5, which is not in B1. Then we're going to construct G5. Okay. Now the variable set, we're going to add the starting symbol to B1. Okay. And the terminal set would be the same terminal set of P1. Okay. The production of P5 would be the same production of P1. Okay. So what should we modify P5 so that it can generate star closure?
So S5 goes to P1 S5 lambda.
Okay. Anyone else? So you're gonna do that, right? So let's say from S5, you're gonna call S1 and depend on S5. Okay. So this basically also show that this closure of the proof is that it also closes the star closure. Okay. Here's the thing: 8.4 saying that the family of context-free language is not closed under intersection of communication. If you see this on the final exam, you try to prove by showing the PDA, and you show by creating a context-free grammar. So you're going to get 0. Okay. I'm running out of time, so I'm going to show you that the intersection of the two context-free does not necessarily produce a context-free language. So how do we show that it's the case? So by contradiction, right? So if it's, the theorem is saying that it's true for all cases, but if we can show one case that is not the case, then it's not closed on the intersection, right? So consider the following languages. Let's say L1, A to the N, B to the N, C to the N. Okay? And L2 is A to the N, B to the N, and C to the N. Again, the notion here that we have two different superscripts, right? In and M. And if you recall from your earlier homework, you were able to construct a context-free grammar when we have different superscripts, right? So now, if we perform the intersection between L1 and L2, so by this time we know that L1 and L2 they are context-free, okay? Because we can show that it can be generated by either the PDA or by the context-free grammar. Okay, now let's do the intersection. So L3 would be this guy. Okay, A to the N, B to the N, C to the N. What did we just show earlier?
That
it's not context-free. By using a pumping lemma. I'm running out of time. Oh no, okay, I'm gonna stop here. We pick up on Monday. Then I'm gonna quickly show you Turing machine. And we're gonna talk about the hierarchy of formal languages. And we're gonna talk about the limitation of theory computing. And we will conclude this class. We're gonna have final. Okay, any questions? All right, I'll see you Monday.
Bye. Thank you, Professor Boy.
Thank you, Professor.
Thank you. Have a nice weekend.
Pleasure. See you later. Have a nice weekend.
Bye.